Should I start? I can start now. Yes. Yeah. So good afternoon to all of you, and who are attending this particular session. And here, uh, okay, I think. Okay. So this particular live interactive session, I think that you have given some queries also, and that we'll try to look that what kind of the queries are related to this particular course. And before that, I just like to say a few things attending this particular course. First, you try to know the course content, what you have to share with you. And along with that, this solution of the assignment, because there are so many assignment problems. So just make clear that what concept can be utilized or basically have utilized solve a particular assignment problem. Now, before interacting with you, I'm just trying to share my same activities and discuss with that first part. This course is advances in welding and joining processes. I think you heard that there are so many applications of the welding processes, and you can see most of the cases we can find out all this kind of exercise by trial and error method. So without much understanding of the process, their applications, their limitations, these aspects. But in this particular course, I'm just trying to present the subject organized way such that you'll be able to some understanding of the process and finally to apply to solve the problem. So that's why this course is designed with the following modules. First is the very fundamentals, the different welding and joining technology, and the surrounding elements. For example, what kind of the range of the current we can apply, what kind of the different welding process applicable for what kind of the environment and what kind of the different types of materials. So that's the first thing I started with that. Next, most widely and most precisely welding technology can be done in laser and electron beam welding process. So there, in this particular module, I have tried to cover this laser and electron beam welding process, and apart from that, we nowadays there is a lots of evolving in the solid state welding process, because there are so many defects and environmental issues associated with the fusion welding process can be eliminated in solid state welding processes. So now, so many works has been focused on the developing of different solid state welding processes. So that is the third module. Next module, we have tried to understand the calculation of the different temperatures and maybe the power requirement associated with the welding process. Okay, so that's why this particular module is termed as computational welding mechanics. So here some basic mathematical calculation I have tried to cover here. Next is the micro joining and nano joining. Nowadays, that there are so many different welding technologies has been developed, and that is associated with a very small scale of the. So that's why specifically I'm talking about the different medical industry. The requirement of the micro joining, or basically micro component, how to join micro. All these aspects are over in this particular module. Next, welding metallurgy. Metallurgy is to some extent that the materials here, the structure, microstructure, and that is very important, because without some point of time we normally part welding understanding the microstructural aspect. But for a long run, to understand or maybe life of a welded joint, to some extent depend on the well-defined microstructure, and that understanding is possible once we go through this particular module, welding metallurgy. And then apart from this thing, now there are so many components and so many applications where we can find out the welding and joining for the non-metallic materials also required, or to some extent the joining between metals to non-metals. So that kind of the issues associated with this different combination of the materials are I have tried to address in this particular. And finally, even how welding technology, understanding the metal transfer can be converted to the most now that advanced manufacturing process. If you can say that additive manufacturing process has been developed. So this particular module I have tried to focus on that, from how to shift from welding to additive manufacturing process. So that's the overall structure of the welding processes, and all the different aspects of different welding processes we have tried to cover in this particular courses. Now, once you look into that, maybe I didn't find that not much of the queries, whatever you feel this Excel sheet, but one has asked already, why cannot we achieve the spray kind of the mode of the metal transfer in GMAW with 100% CO2 as a shielding gas? Okay. So the answer for this particular question is that maybe the metal transfer in a gas metal arc-welding process. So here, the wire is the integral part of the welding system. So metal transfer is not exactly not decided by only the shielding gas. So there are so many other factors that actually dominates the different types of the metal transfer gas metal arc-welding process. But of course, shielding gas also having some role, but that is the minor. But I can say that that is the secondary aspect or secondary cause to influence on the metal transfer at the shielding gas. So we'll discuss about this thing, this particular question further. Next, on ask the flux core arc welding. Here, current is much more because area is low because of hollow inside. That's true also. But then why we increase the current for shielded metal arc welding with increase in the area, basically cross section area of the shielding rod. So therefore, in that case, maybe it's not exactly here. The resistance is not the issue, and in shielded metal arc welding rod. Here, when you increase the diameter of the rod, then you need to melt more amount of the metal. I think I need to say that per unit time, total volume or melting rate is much more once you increase the diameter of the wire, so or diameter of the electrode. So in that case, you need to maintain the high volume rate, melting rate of the electrode. You need to apply more amount of the current, otherwise you will not be able to melt it. So that means you have to increase the current density, and current density can be increased for a fixed area if we increase the current on. So current density increases, the rate of metal transfer will be more. So quickly, of course, there is a static balance exists, that what are the feed rate of the wire and the melting rate, that is always has to be maintained, and it's actually decided by the arc, mainly the arc and voltage, other than the secondary factor like tilting gas and other factors also is not important, but here the primary factor is the current, voltage, feed rate, and the three different parameters that actually control the whole process. And you will discuss this. But from this thing, if you follow that reference book, what we have mentioned in this particular course, try to look into the reference books, and each and individual module you can get in details if you follow the individual references. For example, if you understand the very fundamental understanding of the welding process, then you try to follow the first reference book. For first and even for second also, both. If you are interested in very micro joining, small scale joining processes, then you should follow the third reference. If you are interested in laser only, laser system or laser welding process, processes, you should follow the reference number 4. If you try to a material side, you understand, you focus on the understanding of the different structures, solidification, behavior, all these aspects associated to the welding, then you should follow the reference book 5. These all are the individual reference books as their merit, and it's a standalone books. If you're interested in different calculation, temperature, distribution, stress part, then you should follow the computational welding mechanics book, that is in the reference number 6. Even if you are looking, you try to look into the what are the different advancement, different issues associated with the solid state welding process, specifically the fixed and state welding process, then you should go for book number 7. And if you further advance different kind of the material, difficult to weld material, and what kind of the advanced welding process has been developed for this kind of the different types of the materials, then you can go through this reference number 8. Even finally, if you look into that further, the different finite element modeling or heat source model and other kind of the sample calculation can be done associated with the welding process. Then you can go through reference number 9. And finally, if you are interested in additive manufacturing process, you can go for reference number 10. So each and every reference is important, and all individual references are associated with a particular module. Okay. So that will give the good idea or understanding one particular area if you follow all these kind of the references. Then these are I observed in the last few years that most of the questions associated with the welding process, that what will be the pattern of the exam. That is maybe the most of the cases, that is the first question, what will be the pattern of the exam. Will it be MCQ based or is it pen paper exam? So it is already declared that this pattern of the exam will be multiple choice type questions. That means you have the one question against one question. There are 4 different choices. You choose the correct. So all kind of the only this type of the questions can be here also, and few cases it may be possibility that you need to fill the some calculation, and you have to fill in the blanks type of the questions. But what I remember in my course, here all you can expect that all kind of the MCQ questions will appear in the exam. And It will not be any pen paper exam. I think it will be online exam. You have to choose the correct answer only. But of course, there will be some numerical problems, some mathematical problems, some theoretical basic understanding of the theory, all will be covered. And in certain cases also you need to follow the pattern of the questions that was given in the assignment. You try to be very clearly clear your concept by solving the assignment problem. That is very important. Next question is that if two materials with different densities are welded, how will be the weld heat formula gets changed? We'll discuss that basically what way we can estimate the heat input during the welding process. What will happen when we use the AC current for the welding process? That is the next question. We'll discuss that in different module. Then what software is used for the simulation of the welding process that the students can possibly access? Are these software is frequently the fabrication division of the industry, or are welds mostly modeled through FEM? Actually, software, when it's modeled using the software, they also follow certain tool. Tool means I am feeling that maybe finite element method is a tool here. So that tool most of the software follows. For example, Abacus, they use the this finite element method. Console software, they use the finite element method, and they can solve the welding. Even there is a sys weld that is specifically dedicated for the different welding process. So there also you can find out the tool is normally used is a finite element method most of the cases, and even sys weld can be more dedicated to the welding problem. So in that case, it's might be useful in case of for the industry. But if you want to develop something associated with the welding process, then in that case, it's better to use the very general purpose software. For example, Abacus and COMSOL, these are the general purpose software. You can solve the different kind of the problem, not only the welding problem, but other kind of the problem can be solved using this kind of the software. That why when more heat is generated in the electrode and when the work is, definitely I'll discuss this part. The next question. Apart from this thing, can the metal of fixture will reflect the beam even metal A and metal B same? So that I'll also discuss in the next few slides. I assume that this part is covered, the fundamentals of welding and joining and laser and electron beam welding process. Maybe these two parts is already covered. So I'll try to discuss the topic associated with this two particular area. Now, if you understand the physics of the arc welding process, so there is a metallic plate is there, and you make a circuit, apply the current and voltage there. And normally in welding process, we apply the current is very high, but voltage is very low, not like our domestic line 240 volt is not required here. So anyway, the supply is that kind of is required, but during welding, we don't need that much of the voltage. Maybe voltage is very low, maybe 20 volt is enough, but current can be very high. So that's why in that case, maybe different polarity we normally use. For example, DC plus direct current or AC current can also be used, and this thing, and that is the different welding machines having the different capability. Either you have the source converting to direct current, converting to AC current also. And here, definitely creates the electrical circuit, and that electrical circuit is basically the electrical energy is converted to the thermal energy by creating the arc between the positive one. Either we can put in the positive side to the workpiece and negative to the electrode, or other way also negative to the electrode and positive to the workpiece. So definitely, when there is a flow of the current, it creates the arc, and arc melt the material, and that material further try to join the two components, metallic components, and after solidification, we'll get the final weld joint. Now, basically here the electrical energy is converted to the thermal energy. So definitely during the conversion, there must be some amount of the heat loss from the surface, because due to the convection and radiation from the surface. Okay. So polarity means maybe here DC plus and DC minus, direct current electrode negative. So electrode negative and workpiece positive. If you put in this way, the polarity, if we choose the electrode negative and the workpiece as a positive, the flow of the electron will be attracted to the positive workpiece. So in that case, when the flow of the electron will be attracted by the positive workpiece, so there will be the release the kinetic energy of the electron. Then that electron, in that case, So more amount of the energy will be released to the workpiece. We can say that approximately 30% heat will be generated to the electrode and 70% heat will be generated to the workpiece material. That is the basic simple calculation. Now if you change the polarity, if it is the direct current electrode positive and workpiece negative, in that cases it will be the opposite. The heat generation amount will be just opposite. So 30% heat will be generated to the workpiece and electrode. There will be the 70% heat generation will be there. Now, when you are trying to join the without using any kind of the filler material in a welding process, or maybe non-consumable electrode, for example, gas structures or welding process. In that case, it is better to keep the workpiece as a positive terminal and electrode as a negative terminal, because in that case the electrode is non-consumable. So more better to keep the minimum amount of the heat generation to the electrode side and maximum amount of the heat generation to the workpiece side. But if you use the gas metal arc welding process, for example, here the consumable electrode utilizing, then if more amount of the heat is generated to the electrode side, the electrode consumption will be more in that case. That means easier to maintain the melting rate of the electrode. So in that case, just opposite polarity we can use. In that case, we can use the electrode positive and workpiece as a negative. It means the DC plus direct current electrode positive. This polarity we normally use. But if you use the AC current, in that case there is an alternating current, means there is a reversal of the heat generation from the workpiece and the electrode. So specifically, the material having high affinity to form the oxides, for example, aluminum, they quickly form the oxides, and it's very difficult to remove the oxides also during welding process. So in that case, the alternating current will be more usable, because more or less almost in that case the heating 50% heating with the workpiece occurs, and then next cycle there is a heating of the electrode will occur. So with this alternating way, the more cleaning action as well as the welding action both will be possible in case of the material, low melting point material having the high affinity to form the oxides. So in that case, aluminum is more suitable in case of the AC current. So in that case, we can use the AC current specifically when you try to do the joining of aluminum. Anyway, in fusion welding for aluminum itself is difficult, not like easier as compared to the steel. So there may be the other method can also be used. So that's why for aluminum welding nowadays, people try to use the solid state welding process. Mostly friction state welding process can be utilized. Now I have asked the role of the shielding gas. So definitely the purpose of using the shielding gas in a welding process is the protecting the arc and the molten weld from the contamination by the outside atmosphere. So sometimes we can use the directly shielding gas we can use, or sometimes we can use the slag coverage by the chemical reaction in the arc. So they create the slag formation which is lighted in the weld, and that is on the top, and it protects the molten pool for the contamination of the outside atmosphere. So both way shielding can be provided, but once we talking about the shielding gases, mostly the inner type of gas is preferred to use the argon, helium. They normally used in case most of the cases, but sometimes we can use the carbon dioxide. Carbon dioxide use only the purpose is that the cost of the carbon dioxide is basically cheaper as compared to the inner type of the gas. That is the only purpose to using the carbon dioxide. But most of the commercially available gas metal arc welding process, we can use the carbon dioxide as a shielding gas. And some point, certain cases for particular application or particular material, we can use a combination of the some certain percentage of the argon and certain percentage of the oxygen, or certain the mixing of the two shielding gas can also be used. It entirely depends on the what type of the material we are utilizing. And of course, this shielding gas having the role, but again I am telling the shielding gas having the role on the stability of the arc, but that is a secondary role. Primary role for the metal transfer entirely depend on the current or current density, what current you are utilizing in this particular process. Or maybe you can measure the current density is better in this case, because current density is very high, then it can create the droplet type of the metal, or maybe the small droplet it can create. in case of the gas metal alcoholic process. We'll discuss also different mode of the metal transfer. So here current is the primary factor and sealing gas is the secondary factor here. So we cannot say that if you only change the sealing gas or even you can change the mode of the metal transfer. That may not happen. But of course, certain amount of the roles are there in this case. Here, yes, here you can see that modes of the metal transfer. Specifically, I'm talking of the spray type of the transfer. How it occurs? In this case, the main requirement is the current density is very high than the globular type of the metal transfer. Current density is very high means the current per unit area of the cross-sectional area of the electrode. That should be much more. So high current welding current density is basically melting rate will be much more, and greater pinch force means that opposite to the drop holding forces. So greater pinch force, here some kind of electromagnetic force will be acting, and surface tension force will always try to hold the droplet, molten droplet, and other way the pinch force will try to detach the droplet. So when it's a competition between these two, when greater pinch force is there, then you will try to create more number of the droplets and very rapidly, and pinch up the very quickly and by the high pinch because of the high pinch force. And here, since the droplets are formed very rapidly and very localized area, the droplets is created, and that's why droplets are usually very smaller in size. And this is only possible if you use the high welding current. And once using the high welding current, it actually reduces the but overall temperature increases because high welding current temperature generation will be much more at the electrode. But at the same time, when temperature is very high, it actually lowers the surface tension force. Once surface tension force is the drop holding force, it tries to keep the holding the droplet. So once you lower the drop holding force means the other force are dominating. So very quickly, then droplet can be created. So that's why here you can find out that at high welding current, there is a kind of the droplet kind of the or spray type of the metal transfer is possible. So it is nothing to do with the choice of the sealing gas and whatever way you can manipulate the sealing gas. That may not much influence, but of course certain influence will be there, but it is not up to that extent. It will influence the mode of the metal. It cannot change the mode of the metal transfer. Now, sometimes we confuse that what can be the enthalpy of metal, what is the amount of the heat required to join the material. So heat required to melt is particular given volume of the weld. It actually depends on the two things. One is the heat required first to melt. Melt means basically there is a transformation of the phase from solid phase to liquid phase. Okay. But in that case, once we raise the room temperature to the melting temperature, and second amount of the heat, latent heat also required to change the phase from the solid phase to liquid phase. So both has to be accounted, and combining these two is actually required amount of the heat for a given volume of the oil. So we can calculate what is the heat required for a given volume of the oil. Rho Cp specific heat melting that from room initial temperature to the melting temperature, that is amount of the heat is required, and that is associated with specific heat plus what is the latent heat to change the phase from liquid phase to solid phase. That heat has to be accounted. So combining these two actually required to the melt for a given volume of the oil. So be careful, but in a specific oil domain we can define the different zones. One is the fusion zone, heat affected zone, base material we can define, and here the fusion zone, heat affected zone, and base material. Sometimes we try to look into the fluid flow also. The surface active elements. Surface active elements actually modify the oil pool shape. An organized way we can utilize the surface active elements in the beneficial way we can utilize it. For example, it actually when there is a application of the surface active elements, it actually try to change the material flow pattern within the small oil pool, molten oil pool. So here, and that flow pattern actually decides the fusion zone, shape of the fusion zone. So dominant driving force for the fluid flow, the material flow is mainly the surface tension force. So basically, surface active elements actually modify the nature of the surface tension gradient, and once the surface tension gradient changes, it influences the flow pattern. So it can change even there is a direction of the surface tension gradient, positive to negative or negative to positive. So that gradient actually decides the flow of the molten material from one point to another point. Okay, we'll some example. So that is the main role of the surface active elements, just to change the surface tension gradient. And finally, surface tension gradient change the flow pattern. And once there is a change in the flow pattern, that actually change the shape of the fusion zone. But we can utilize in this case in such a way that here you can able to understand that what way the surface tension actually acts. Okay, sometimes it is called the Marangoni convection also. First, magnitude and the direction of the surface tension gradients. So that is associated with the Marangoni convection of the convective flow of the liquid molten pool from one side to another. So first case is if you see there is a negative surface tension gradient. Okay, that actually create the usually oil pool is the aspect ratio, the different aspect ratio. In that case, the depth of penetration is low and width is much more, and it actually decides the flow pattern, and from center to outward periphery there is a flow of the molten metal occurs. And other way, very small addition of the surface active elements change the surface tension gradient, and in that case the surface tension gradient can be positive. Once it is done, then the shape, accordingly the shape of the oil pool will be like that. The material flow pattern from center, from outward periphery towards the center. So in that case, it actually increases the oil depth and decreases the oil width. So therefore, material can be same. All welding process parameter can be the same, but only thing is difference can be the one particular in this particular material. There is an application of the small amount of the surface active elements, but you can expect the shape of the oil pool can be different. So the second case, we can utilize this thing as a beneficial way in that, because in that case it is possible to reach the high depth of penetration even for arc welding process and very low width, which is practically most useful as compared to the flat pattern of the oil pool. So that's why there is the use of the surface active element. But surface active element can be used in the different way. Maybe in certain cases the small amounts of the oxygen and sulfur may be present within the liquid metal that can act as a surface active elements. But of course, it is having some optimum value. Not any amount of the sulfur may not act as a surface active element. There is some specific amount of the sulfur or oxygen can act as a surface active element, and it can change the welding oil pool shape. Okay, here I can give some example also there. For example, you can change the chemical composition of the base metal, simply addition of the small amount of the sulfur. But sometimes the flux can be used on the substrates, halides or oxides flux. Spreading of the flux over the surface, simply paint it using these particular fluxes, and that can act as surface active elements. Or sometimes along with the sealing gas, you can have small addition of the CO2. For example, small addition of the carbon dioxide to the argon sealing gas can act as a surface active element. So all the different ways there is application of the surface active elements, and once we make is the controlled way, then industrially activated TIG welding process has been developed. It's a modified version of the TIG or gas metal arc welding process. So here is the application of the surface active elements in the beneficial way, and accordingly the different welding process has been developed. Okay, so I'm not going into that is the purpose of this thing. And sometimes we can ask the electron beam welding of the dissimilar. If we discuss the electron beam welding of the dissimilar material, so what happened? What the particular point here? That sometimes the residual magnetism of the weldment in the fixture can be the ferromagnetic material. Okay, and in that case there is a flow of the electron in electron beam welding process. Okay, but if there is a thermoelectric magnetic field actually cause there is a temperature gradient in the dissimilar material because of the Seebeck effect. So once this Seebeck effect will be active, once this is a material A and material B are different, so basically dissimilar material talking about, if it is similar material then it will not Seebeck effect will not be effective here. So once there is a dissimilar material, what may happen that when you are focusing on the electron beam at the interface, there may be the possibility of the deflection of the electron beam one of the side of the material, one-sided, because the magnetic permeability of these two cases are there, and here the Seebeck effect will act into here. So then it will be difficult to join for the dissimilar metal using the electron beam welding process. So this is the just point. For example, sets of the dissimilar, for example, iron and copper, SS304 and low carbon steel and copper, nickel, all this combination of the materials can have this kind of the Seebeck effect, and then the electron beam, the beam profile can be deflected in one of the positions. So you'll get the very good result of welding weld joint. Now there is another point I want to discuss. Sometimes we try to look into the is a comparative comparison between the laser and electron beam welding process. Here you can see that weld joint has, in terms of that shape, the electron beam welding process we know very smaller or narrow, but in case of the laser welding also very narrow and smaller, but it is more the narrower or more smaller, width is very low as compared to the laser welding process. Penetration, you're talking about the penetration, the deep penetration we can expect in case of the electron beam welding process, but laser welding lack of penetration means it's not that much of electron beam welding process. Okay, so in that case, very high thickness material if you want to join, then electron beam welding is preferred than laser beam welding process. Welding speed. So electron beam welding process can scan the electron beam with very high speed as compared to the laser. Shielding gas, because electron beam welding process we know it is under the vacuum, all operations can be done, but here there is no need of any shielding gas. But in case of the laser welding process, nitrogen or argon shielding gas can be used. Vacuum chamber, in case of electron beam there is no that is required, but laser beam welding process it is not required, because laser beam you can using the shielding gas. Cost, but cost of the electron beam welding system is very high as compared to the laser welding process. Generation of X-ray in electron beam welding process it is possible, but not possible in the laser welding process. But our efficiency is more in case of the electron beam welding process as compared to that laser welding, it's a very low. Size of the workpiece, that means since it's a electron beam welding process is normally performed under the vacuum chamber, so size of the workpiece is limited by the size of the chamber. But there is no such limitation in case of the laser welding process. It's open, and here focusing the laser along the coaxially, you can focus that shielding gas also. So in that case, there is no limitation of the size of the component. So these are the basic differences between the electron beam and laser beam welding process. But which cases I am telling that it's a maybe lack of penetration, but this penetration is much more laser welding process as compared to the arc welding process. So laser can be used the arc welding process in the better way. So I think that's all discussion. Now we can have any query, we can discuss further also. Process as compared to okay. So any query maybe you can ask. What I can see from this thing that whatever there is I think there is sometimes there is some network issue, but I can see the sound is okay, fine. I'm just looking in my using my own speaker. Okay, now someone asking Anshul Sharma, how to fill the undercut weld zone specifically during the end of run. Okay, so in that case, simply very simple way, that undercut zone, you just make the consumable electrode, any part of consumable electrode. Make deposits on the deposits on the zone, and then I think you can, in that way you can fill the undercut zone. I study computer science. Can learning about welding and joining help me getting a job at some shop? Surya, this course runs live daily or recorded video? No, this course is not run live daily. Already recorded video are there that can be utilized. Why or how high frequency current put to electrode together the arc generation? Can you more clarify this thing? What you exactly want to know? So in welding, I already discussed that welding process, how it works. You have the main supply is the maybe the 50 hertz cycle frequency, 40 volt. Okay, so that is converted to the very low voltage and very high current. Okay. And I think the voltage that is the this high. Yes. So that high current actually application of the high current, and initially you can the kind of the self starter is normally you can utilize there, and then we can create the arc initially, and then continuously there is the arc, and this arc is basically maintained by making the constant gap between the electron workpiece. Please give an example of the best way to join aluminum parts. Best way to join aluminum parts is you follow any kind of the solid state joining process. Any kind of, mainly you can use the friction stir welding process also. So that is the best way to join the aluminum, because fusion welding in the aluminum, there are so many problems. I mean, with the Kundan theory, I mean without touching the parent material. Definitely without touching the parent material, there is a self-starter kind of. Okay, what you can use you can utilize this thing, the main mechanism you can utilize in the bike also, the self-starter initially, create the arc. So once you create the arc, initially, the purging the very high current initially. Once the arc is created, then gradually to be maintained. So I already told that gap can be maintained. Gap can be constant. Very low gap, maybe 2 millimeter maximum, 1 to 2 millimeter. You can, yes, George, if you join an aluminum part even for fixed stir welding process, you can achieve close to the almost 100% joint strength. It's possible to achieve using the aluminum, but in that case, you have to find out the optimized set of the parameters. If needed, maybe I know if very specific alloy you can utilize for aluminum alloy. There may be some preheating can be done also in the aluminum before joining. Then joint strength will be much better as compared to the without any heating. Okay. Kundan theory, I think this course is basically not exactly the practicing and all this thing or welding engineer. Of course, you get some basic fundamental understanding, but if you want to enter into details, any kind of specifically what kind of the symbols and what industry people what way they are utilizing this thing, that is how can you inspect this thing. That is the different aspect, but that is not actually covered in this particular course. Okay, so then in that case you need to go through some other courses. So you'll get maybe some standardization. They are following certain standardization, ASME or some other standardization there, or American Welding Journal, AWS, their standard, some their standard. So that's different. Okay, I think there are a few guests also. Adis M. You want to interact? D. Kumaraswamy. I'm just looking into through MS Team. हमारे डॉक्यूमेंट्स है सही तरह think live interaction session is done. Please stop this one. And thank you very much for your for attending this particular live interaction session. Okay. Now, if anyone is interested to look into the through MS Team also, they can interact. Just keep it open, the MS Team. The NPL team, please switch this live interaction can be closed. But if you have MS Team also, you can discuss further if there is a need.